So it's a great pleasure today to have Tianqi Chen give the guest lecture for CS 159, Data-Driven Algorithms Design. Tianqi recently completed his PhD at the University of Washington, where he worked on machine learning systems, machine learning for systems, and vice versa. He'll be joining Carnegie Mellon University as assistant professor in the fall. He's currently taking his gap year at a startup. Tianqi and I, a bit of trivia, we actually are academic siblings. We both went through Carlos Gestrin's lab, Tianqi as a PhD student, myself as a postdoc, although I guess many years apart. And today, Tianqi will be giving an overview of his thesis work. Take it away, Tianqi.
Yeah, thanks, Yisheng, for the introduction. So, hello, everyone. My name is Tianqi Chen. So, today I'm going to tell you a bit about my thesis work, in particular titles about elements of learning systems. So, as you all know, that machine learning is being quite ubiquitous, and there are a lot of applications that we're trying to apply machine learning to, including things like voice recognition, natural language processing, self-driving car and computer vision, and scientific data analytics. And it's always interesting to ask, at this stage, it's kind of like a golden age for machine learning, and how did we get there? So if you look back at the history, you can find there are a few elements that really affected the success of the machine learning today. If you look at machine learning research, actually machine learning research started quite early, as early as 1960s when the perception algorithm got invented. So or even you can even count earlier if you count the history of statistical machine learning. Around year 2000, many of the algorithms we're using today, including things like gradient boosting machines, ConvNet, support vector machine, LSTM, are already invented. And around the same time, we will start to see a boom of internet and web, and companies like Google, Facebook, Wikipedia, and Flickr, and services like Wikipedia that start to curate data and collect data from the web. So all those data becomes a rich field for machine learning, and we start to see organized competitions like Netflix Challenge, Kaggle, and ImageNet, and those data set from a web really help us to create these challenges. And if you look at those challenges, many of them are actually the cause of the revolution stages in machine learning. For example, the Netflix challenge really started a new era of machine learning for recommender assistance, and ImageNet really was starts the beginning of the deep learning area of the computer vision. If you look at the data set we are having today, they are becoming more and more diverse. So you can collect data from your watches, your phones, your cars, and the data not only come from web anymore, they also come from our daily sensors and other things. And it creates new interesting challenges on how to deal with data, including things like privacy issue, how to store them, and how can we make effective learning on those data sets. The rich data set in machine learning creates a huge demand for compute, and that creates a third axis in here. So around 2006, the availability of public cloud really helped us to be able to do distributed machine learning easily and scale up our computations. Machine learning researchers started to use GPUs around 2009, when a group of researchers from engineering groups starts to try to use a GPU for accelerating deep learning computation. Today, GPU is still the powerhouse that drives many of the deep learning applications today. And as we start to see the hardware trend, it's interesting to see companies starting to design new variants of hardware. The most typical example is Google's TPU, as well as many other hardware accelerators that try to design specialized instructions to accelerate machine learning execution workloads. And the availability of those specialized hardware also brings interesting challenge on how can we program those hardware effectively. So if you look at these three axes, the machine learning model research, data, and compute are really the three pillars that drives the success of machine learning in nowadays. However, there's still one missing ingredient in here, and that's the last axis. So about 10 years ago, I was a graduate. I was like an undergraduate researcher, and I started to work on deep learning. And at that time, I need to spend about 3 months to handwrite CUDA kernels in order to put my convolution restricted Boltzmann machine on the GTX 2080 card then. Today, we only have to write a few lines of Python code to do that. So such huge difference is really thanks to the arrival of machine learning systems. In particular, starts 2010, we started to see a wide range of machine learning systems arriving on the market. For example, there are GraphLab for general purpose graph processing, Apache Spark for data analytics, Scikit-learn for general purpose machine learning, Caffe, the first generation of deep learning system, XGBoost for gradient tree boosting, and ResNet, TensorFlow, and PyTorch for the current generation of deep learning system. All those systems really enables researchers to describe their high-level ideas in a few lines of Python code while being able to offload all those computation workloads onto those modern hardwares, including GPUs and in the future TPUs. So I've been working on a few of those learning systems. Today, I'm going to tell you about the high-level stories behind them. I'm going to briefly talk about the first two systems, XGBoost and ResNet, and I'm going to spend majority of my time talking about the last system, TVM. So I will start to talk about XGBoost. So XGBoost, in a nutshell, it's a scalable tree boosting system. So the idea is that we want to effectively speed up algorithm called gradient tree boosting that tries to combine multiple weak decision trees into a strong predictor. There are a few highlights of XGBoost, but since we released it about 7 years ago now, it have started to become a de facto tool for data science. For example, have been used by more than half of Kaggle winning solutions in the past few years. And one interesting fact is it's also being used to analyze scientific data. The scientists in CERN actually used XGBoost to analyze interesting physical events from a large hadron collider. And it has been used by major companies, including Google Cloud, AWS, Uber, and Airbnb. There are several technical highlights that XGBoost offers. First of all, from a learning perspective, we build an algorithm that help us to automatically handle missing values, and build an algorithm that allows us to be aware of the sparsity in the training data, so that we can, effectively train over sparse data set. And on the system side, we build a few optimizations so that we can make effective use of the compute caches on the target machine. I want to specifically talk about one interesting ingredient in here. So it's about automatically missing value handling in our applications. So when you start to look at machine learning applications, usually machine learning, the first step of feeding data into a model is to do data cleanups so that you can clean up missing values and impute the values that you don't know about. However, in reality, that's a really tedious step, and it's not not everybody knows how to do that. And even worse, not everybody knows how to do that correctly. So in XGBoost, actually, we try to introduce a step to help us to automatically handle missing value. The idea is that we'll build decision trees that try to make decisions on each of the branches. But besides the decision on the feature values, we also have a default missing value direction. That means that, for example, if V1 is missing, it will go through the red direction on the left, and V2 is missing, it will go to the red direction on the right. And more importantly, we are learning those default directions together with the decision boundaries of decision tree together, so that we can learn to find the best default direction on each of the branches. By combining these two approaches, users no longer have to worry about missing values, and they can directly feed the data with missing values to XGBoost, and the algorithm will be able to automatically handle it for you. And during prediction time, it will try to be able to predict using the rules learned from a training time. So one important insight we learned from this feature is that it's really important to develop machine learning algorithms that are accessible. In this case, not all the data scientists knows how to process and clean up data. And by making the algorithm accessible to those who don't know how to do that, actually we made a huge impact. And this is by far one of the most widely used feature in XGBoost today. The second system I'm going to briefly touch about is ResNet. So And MaxNet is one of the second generation of deep learning system. It is actually one of the first that ever scales to multiple GPUs and is currently adopted by Amazon. And I'm going to talk about one particular interesting technical highlights that we developed in MaxNet. This is the problem that how can we train very deep neural networks with very limited memory. So as you can hear about a common joke that the deepest ResNet you can ever train on GPUs are always ResNet 200. The reason is that 200 layers are really the maximum amount of layers you can put onto the GPU. As we are starting to try bigger data sets, it's always interesting to try bigger models. However, we are usually bounded by the amount of GPU compute memory that the device can offer. So the question is, can we train deeper neural networks on the limited GPU memory? The answer is actually positive. So the idea is that we want to try to develop a variant of backpropagation algorithm that does not scale linearly with number of layers. So if you do a traditional backpropagation or automatic differentiation, what you will do is as follows. You will first do forward propagation on your neural network, and you will need to record all the colored nodes in the intermediate computation so that when you do backprop, you can make use of those colored nodes to compute the gradient in the backward parse. So in our new algorithm, instead of trying to keep track of every intermediate computation, what we do is we will try to skip some of the computations. So only the colored nodes will be recorded, and the blank node will be, so we will immediately deallocate the memory after we compute the blank node. So now when we're trying to do backpropagation, what we're doing instead is that because we no longer have a blank node in the first graph, so we want to recompute some of the nodes. So we will first do a recomputation pass of the small mini segment, and then you can do backpropagation on this mini segment. And after you do that, you can do recomputation again on the second segment, and then you can do backpropagation on second segment. So you get idea in here. More importantly, when we're doing backpropagation on the second segment, you can actually free the memories you use for the backpropagation, mini backpropagation of the first segment. So your overall memory cost will be the combination of the memory cost that you need to store the color node in the forward pass, which is O of k, and the cost you will need to perform those mini backpropagations, which is cost of n divided by k. So if you choose k smartly, you can find that you will get a square root of number of layers memory complexity. And so by using this algorithm, we can find that we can really scale up the number of layers that you can have on this on this backend. In particular, we'll be able to train 1,000-layer ResNet on a single GPU, which is not possible before. So I briefly talk about XGBoost and MaxNet. I'm going to talk about TVM, which is the more recent system we built. So if we summarize XGBoost and MaxNet, what you'll find is that both of them are systems that enable machine learning algorithms. However, one of the untold story behind all those learning systems is that we will need to spend a lot of engineering effort to go and optimize those learning systems. And I spent more than 3 years of my PhD doing that, and that makes me question that do we really want to do that? In particular, since machine learning is that awesome, can we try to use machine learning to optimize systems themselves instead? And so that brings us to the TVM system, and the answer is positive. So the idea is we want to introduce a new paradigm called learning-based learning system that not only tries to be a system that enables machine learning, but also use machine learning to optimize those systems instead. As a result, we can spend less engineering effort on building those systems. So I'm going to use TVM as a particular example of learning-based learning system. In particular, I'm going to first talk about why do we need this kind of new approaches to optimize learning systems, and then I'm going to briefly touch about how we can build machine learning algorithms to optimize those learning system workloads. And finally, we are going to talk about how we can build end-to-end learning system that can be deployed to the wild today. So the general problem that TVM tries to solve is to deploy machine learning models onto a wide variety of hardware backends. And so how do we start to work on this problem? Actually, 3 years ago, I have a collaborator who is a computer architect. His name's Terry. He came to me and said, hey, Tianqi, I'm working on this awesome deep learning accelerators. Do you want to work together? I said, sure. Machine learning accelerator like TPU seems to be a future. How do I put my copy detector on top of it? And then he give me this entire page of microassembly manual on how to program the accelerator. You can see that you don't have to read it, but from a far look at it, you can see it's very complicated to program. And I really miss my days of writing Python when working on this project. So that's why we build. That's what motivated us to build a new system called TVM that tries to bridge the gap between the modern machine learning frameworks and all those hardware accelerators, including your data center CPU, GPUs, Raspberry Pis, embedded devices, and TPU-like accelerators. So before I talk about our approach, let's start to review a bit of what existing frameworks do. So most of the existing deep learning frameworks will express the computations of a deep learning model in what we call a computational graph or high-level data flow graph. What's special about those data flow graph is that each of a color node here corresponds to primitive tensor operations such as matrix multiplication or high-dimensional convolution. In order to offload those computations onto low-level hardware, what we'll do is we'll offload some of the color node into low-level libraries, such as in the case of Nvidia, there's a library called CUDN, which is heavily optimized by Nvidia engineers on those platforms. So what is the problem of taking this approach? The problem is that for each of the color node in the high-level framework, there has to be a correspondence in the low-level CUDN library. As you know, that machine learning is a fast-evolving field, and we will start to increasingly add new operators. And there will be a problem of missing operators when they occur. And another possible thing that will happen is that as people start to optimize those workloads, people might want to trying to do system optimizations that takes a few of the color node here and fuse them onto a new node. This fused node will execute together on the GPUs, and it will bring potential, speed up benefit. In many cases, 1.5x. The problem now, however, is that this new blue node no longer exists in the low-level CUDN library. So what do you do? One of the typical approach that people will do is they will go and call Nvidia and say, hey, please implement this blue node on your library. We did that a few years ago, and it took Nvidia about 1 year to get back to us and implement that library. Another way to do that is just go and implement it in CUDA by yourself. However, that means that you will need additional engineering effort. And if you multiply that by amount of hardware backend you will support, you can imagine it's a very engineering intensive process, and only the very big companies can afford to do that. So how can we do it more smartly? The idea is they want to develop a new system that replaces those human effort and trying to be able to automatically optimize and generate programs to support those high-level color nodes in the high-level computational graph. As a result, we don't have to spend as many engineering effort on optimizing those workloads. So I'm going to briefly talk about how can we build machine learning algorithms to optimize those programs. From a high level, each of the color node will be described as what we call a specification language in tensor expression. The idea is that we will describe how do we compute each element of the target tensor. The expression looks very like Einstein notation or the index expression on how do you compute a target workload. And in this case, this specification describes how do we compute a transposed matrix multiplication. Then we will try to define a search space of possible program optimizations on top of this specification that generate different low-level program variations. To give you a sense of what kind of low-level program variation can be generated from a specification, we could directly generate vanilla for loop code that implement this transposed matrix multiplication. If you're familiar with CPU-based optimization, you might know that we want to transform a loop a bit so that you have a different iteration order that is more cache-friendly. And as a result, it gives you better speed up on this particular workload. And finally, if you are working with special accelerators, you might want to translate some of the computation onto the special instructions that are supported by the specialized accelerators. So the idea is we will try to build a search space of billions of possible optimization choices, and then trying to use an algorithm to be able to automatically search over that search space to find a best possible optimization for that particular tensor operator. So to formalize the problem a bit, so we can use E to denote the expression and S of E to denote the search space. The goal of AutoTVM is trying to be able to come up with optimization configuration that we can then feed to a code generator. And the code generator will generate a program that we can send to a target hardware platform. Our goal is to minimize the cost of the target platform. Usually it's execution cost, and if you can measure other things like energy cost and memory consumption, they can also become part of the objective function. So there are a few ways we can go and attack this problem. So one of the first way we can do is we can do black box optimization. The idea is we can just try out different configurations over and over again until we find a good one. The problem is that the space, this is quite a big space for trying out different operators. In particular, there are billions of possible choices, and if you want to try millions of them, it's really quite wasteful of time. Alternatively, we can try to do a more cost model driven approach. So the idea is we will borrow conventional wisdom from database community to define approximate cost model called F hat that gives you the approximate cost for a given configuration. And then we pick the best model, pick the best configuration to send to a target hardware. Of course, the challenge here is we need to define reliable cost model for each kind of hardware. Modern hardware is very, very complicated, and go and talk to your computer architecture friend. They will tell you it's really hard to design reliable cost model for the new hardware that are available. So instead, we are taking a more statistical approach, and that's, I think, quite related to what's being taught in this class. The idea is that we'll collect data generated from those code samples, and we'll use them to train a statistical cost model F hat to then use to feedback into AutoTVM for learning. One of the interesting application of this is that we can automatically adapt to hardware types, so we don't have to specify specific information such as cache lines and other information of the hardware in the data set, and they will be learned and picked up automatically by the learning algorithm. Of course, there's one remaining challenge, which is how do we design the effective cost model that is used in the learning process. So if you look at this problem actually looks quite like many other problem settings in machine learning, in particular, the problem set does like a hyperparameter tuning or Bayesian optimization. On the other hand, this problem offers a few quite unique characteristics. In particular, first of all, we have a relatively low experimentation cost. So to profile each of the program runs on the target hardware, it costs you about a second. That means that we can afford to collect quite thousands or even tens of thousands data points to train our cost model. On the other hand, that also means that our learning algorithm have to run very fast. As I say, if your learning algorithm takes more than 10 seconds to complete, I would rather directly go and collect Oracle data as opposed to run the approximate learning algorithm to predict the cost. The second interesting characteristic is that because we are trying to model the cost of programs, we really want to take benefit of the fact and build program-aware cost models. The third interesting factor here is that we are trying to optimize a large quantity of similar tasks. So in the case of optimizing for end-to-end machine learning, deep learning models, there are more than 10 layers in ResNet, and each of the layer is a separate workload, and in this case, a separate learning task. On the other hand, also all those learning tasks are related to each other. So there's a question of how can we do effective multitask learning across all those tasks, so that we don't have to do everything from scratch. So I've already talked about implications of the low experiment cost. Let's start to talk about how we can build a more program-aware modeling on this particular problem. So as a vanilla approach, what we can do is we can directly take those high-level configurations. Some of them correspond to the order of loops, threading choices, and memory scoping choices. Directly flatten them as a feature vector and send them into your favorite cost model. In many cases, can be a neural network, or in my case, gradient tree boosting models. The problem of this approach is that it ignores the domain knowledge that we are doing program-aware modeling. And because different tasks might have different configuration space, actually we can no longer share the same cost model across different tasks. So what we'll do is we'll take one step further. The idea is that we'll first lower the high-level configuration into what we call a low-level abstract syntax tree common representation. And then we'll try to extract features from that common abstract syntax tree representation. And finally, we'll learn a cost model on those statistical features. The advantage of this approach is that the low-level common AST is actually a common representation across all those tasks. That allows us to build a model that is more task invariant and be able to, make use of a cost model across multiple domains. And finally, if you like neural networks, you can also take a more neuron-based approach that uses a tree GRU to encode the abstract syntax tree and gives you the final cost. So if you compare all those three approaches, you can find that both the tree-based model and neuron-based model are task-aware, and they gives you quite good prediction performance. By default, we pick the tree-based model because they have relatively lower time cost than the neuron-based model. So to give you a sense on how effective we can do by using the machine learning-based approach, here's the benchmark on optimizing one particular layer of ResNet on a Titan X GPU. The x-axis is the number of experimental trials on the target hardware that we use to benchmark the workloads. And the y-axis is the relative speed up we can get versus the Nvidia CUDN library. If we do black box optimization, we can find that we can get decent performance after 800 trials. But if you use machine learning-based approach, we can find that we can get better performance faster. The intuition behind is not really because the machine learning is smarter than humans. It's really because humans have to design those libraries that are generic and that works for all kinds of workloads, while machine learning-based approach can specialize to this particular workload so that we can generate code that's specifically optimized for this particular layer of ResNet. And that gives us a lot of advantages in finding better optimization choices.
Hey, Tianqi, I have a quick question.
Yep. Go ahead.
How big of a concern is it to have good coverage in your training data?
Mm-hmm. Yeah, that's an excellent question. So in our case, actually, we are doing like on a loop updates, which means that every 10 trials we'll go back to collect profiling data, and there's also we also have a basic epsilon greedy exploration, so that we don't overfit to the data that we collect. So another interesting perspective about the cost model is the task invariance, and that's very important.
Sorry, there's a question from the class.
Go ahead. Yeah.
Go ahead.
Sorry, I have a quick question. That you mean collecting data? So you mean you need to run the generated code on this hard machine, and then you collect the time cost?
That's correct. Yeah.
Oh, okay.
So one of the last interesting characteristics of our problem is that we have a large quantity of similar tasks. That's become particularly interesting when we start to look at the end-to-end learning tasks. In particular, imagine that we have already collected data for the first 10 layers of ResNet. We want to start to optimize the 11th one. What we really hope to do is we want to be able to make use of those historical data to build a shared cost model that we can directly use to optimize the new task. In order to do that, it's really important to build a task invariant representation. And that's why the tree-based model and neural-based model really help us in this case. So to give a sense on how much gain we can get by turning on this transfer learning node, on this particular workload, if already get training data from the first 10 layers, we want to generalize the 11th layer, you can almost immediately pick up the best performing code from a starting point. Note that it's not always true, and in many cases we will get 3x to 10x speed up versus non-transfer case. That means that we can afford to search over more interesting, bigger search space, and it's more likely that bigger search space will cover what the best human programmer might write. So to recap, there are three interesting characteristics of our problem, including relatively low experiment cost programmable modeling, and multitask learning. If you are interested in more details, you can go ahead and take a look at our newest paper. And one of the interesting things about this setup is that this learning to optimize tensor program is an interesting problem setup that can be used to test many machine learning ideas for optimizing learning system. In particular, you can imagine that we can plug in algorithms such as Bayesian hyperparameter optimization or other bandit-based algorithm to optimize the same application scenario. So to make that easy, we build a distributed test bed to allow others to easily plug in new experiments. So in particular, everyone can run their experiment in Python on the left side, and then we will have a RPC protocol that allows us to send those generated programs onto our remote resources that includes embedded devices as well as server level devices. And in our lab, actually, we build what we call device fleet that contains the collection of different hardware devices that we can test on. So this is actually a Photoshop of a real hardware devices fleet on our lab. You can find that there are a few Raspberry Pis, FPGAs, and mobile devices. Okay, so when we talk about how can we use machine learning to optimize the learning system, let me take back a bit and talk a bit about the other system perspectives about TVM. So AutoTVM is an important part of a much bigger system called TVM, which is an end-to-end deep learning compiler. The idea is that we will build a two-level intermediate representation that allows us to define that rich search space of program optimization, and then we can use machine learning to effectively go and optimize on that program space. So I'm going to particularly talk about how we can build effective optimization search space for low-level programs. So to recap, for each of a high-level tensor expression, we want to define a search space that builds possible mappings from the high-level expression to low-level hardware valid programs. And in here, we actually borrow conventional ideas from existing works in image processing. In particular, there's a work called Halide that tries to define such kind of search space on computer graphics workload. However, the real challenge is how can we define the effective search space so that it covers what a programmer might write. So on CPUs, we can leverage a lot of existing works that build effective loop transformations optimized for cache locality, as well as using vectorization to vectorize the code. One of the more interesting things as we start to look at more weird hardware, including modern GPUs and TPU-like accelerators. So in terms of GPU, one of the interesting perspectives that they have what we call a shared memory system that allows multiple processors to share the same compute memory. And we want to be able to effectively use of that by allowing threads to cooperate with each other. The things become most interesting when we start to look at TPU-like accelerators. So these accelerators are special both in terms of the compute primitive they expose, as well as the memory subsystem they have. In terms of compute primitives, traditionally when you write your Python code or C code, you can just try to specify how to compute each element. This will all call scalar programming. Modern CPUs start to bring in vector computing units. So you have to write your program in a way that compute 4 floating points together, and that brings quite a lot of restrictions in terms of what you can write. And if you look at TPU-like accelerators, TPUs have instructions such as matrix multiplication that directly multiply 2 matrices together. That means that you have to express your computation in the form of those high-dimensional tensor compute primitives. And it really brings challenges how can build system to target those tensor instructions. Because from a high level, users still want to write the specification in Einstein notation, but we really want to be able to target those low-level coarse-grained tensor instructions. So this is a new challenge, what we call tensorization challenge that we introduced to a TVM system. The idea is that we not only want the developer to specify the computation specification in expression language, we also ask the hardware designer to specify their hardware interface via the same tensor expression language. And in here, here's an example of hardware designer specifying the 8x8 vector matrix dot product. And the idea is that we want to develop a tensorization process that takes the specification from the high-level computation and the specification from hardware interface and try to be able to automatically map the high-level computation to the low-level hardware interface specification. Right now, we have a semi-automatic approach to do that. And as in compiler researches, there's a vectorization, which is more limited form of tensorization, have been an active research area in the past 10 years. And we expect that tensorization will be a very interesting research area in the next few years as well. The second interesting perspective about these systems are about the memory subsystem that they expose. In particular, when we're trying to write matrix publication code on those workloads, usually a naive approach is you can just do load the weight input and load the weight, then you do maxmal on your compute unit. On the other hand, modern processors want to have this more like a pipeline approach, where as you do the input weight loading, you want to be able to perform those computations in concurrent with the weight loading. However, in order to do that, modern CPUs actually have smart caching prefetching units, and however, in terms of like modern TPU accelerators, they don't have this kind of smart caches to do prefetching. So what do we do instead is we want to explicitly encode the dependencies from the previous stages to the compute stage. That brings quite a lot of challenges in how can we write those programs. So in order to do that, what we do is we build a transformation path that turns a multi-threaded program onto these low-level programs that can be recognized by the target hardware. So to summarize and recap on this part, the general idea is that we will introduce effective primitives from previous works to optimize for CPUs, and introduce new schedule primitives to give us effective optimization on GPUs and enable TPU-like accelerators. The combination of all those possible optimization choices really gives us a rich search space, and so that we can really use machine learning action to find the optimal choices that are as close to what humans can write.
Quick
so
question.
Go ahead.
So I know that you can measure the total running time by running experiments on hardware. Can you measure running time of subcomponents? I mean, I imagine the cost models that people used before, they just basically put a cost on each subcomponent, and then from that they do stuff. And this black box approach of learning a cost model has benefits and trade-offs, and one can imagine a middle ground is learning these individual modules if you can measure it.
That's an excellent question. So it's not really possible for all the possible hardware, but for cases like, for example, Nvidia hardware, they have performance content profiler. So it's likely that you can use profiling techniques to profile, and it will tell you, for example, what is the memory loading cost, what's the computation cost, and these might become more interesting signals for machine learning. In this case, you can imagine that maybe we can do multi-objective learning where you have different kind of objectives that gives you better signals. So to give a sense on how much performance benefit by putting everything together, here's an end-to-end benchmark on inference workloads on Nvidia GPUs. So the x-axis is the end-to-end running time, so lower is better, and the y-axis is the different kind of workloads. Our baselines are TensorFlow and MXNet, both of which are backed by CUDN library, which is optimized by Nvidia. By using TVM, you can find that we can generate better code end-to-end than the state-of-the-art workloads. If you look at left, on conventional workloads like ResNet 18, we can get pretty good performance, like 1.2x and 1.3x speed up. The most important takeaway, though, is that if you look at far right, on this particular model, DQN model, there's 3x gap here. So what is the reason? So this DQN model is the model used by DeepMind to play Atari game. So one thing that you can imagine that is recognizing puppies is more important than playing games, right? The real reason behind that is because the task or goal of these NVIDIA engineers in COD and team is go and optimize for standard benchmarks, which means that ResNet is their real objective function. On the other hand, if you go and look at nowadays applications, actually there are a lot more interesting machine learning models out there than the standard benchmark. So in some sense, these NVIDIA engineers are overfitting to the benchmarks, while if you can make machine learning action to automatically optimize for all these workloads, we can get state-of-the-art performance on all this kind of new workloads and emerging workloads. And this is very important. And this is one reason why TVM is already widely adopted, because if you go and talk to companies that have driving car, medical imaging, or other kind of cases, almost all of their models are not standard ResNet. And in almost all these cases, you can observe 2x to 3x, sometimes 5x speed up on those workloads. The second interesting thing is we can take the same approach and use machine learning to automatically generate deployable solution on different kind of hardware backend. In this case, we have baselines on the ARM CPU and ARM GPU. And in both cases, you can find that TVM can generate better solutions than the specialized solution on those workloads. You can find that, for example, TensorFlow have a specific solution called TensorFlow Lite on the ARM CPU, and we can get better performance than what TensorFlow Lite can get. So in the beginning of the talk, I mentioned about accelerators. And so far we talked about CPU and GPU and mobile GPU. So what about accelerators? So in the TVM stack, we actually build what we call VTA. It's a specialized deep learning accelerator design stack. The idea is that we'll provide open source microarchitecture design that's a bit like TPU, open source instruction set, and a driver set that directly connects it to the current TVM runtime stack. And you can directly put VTA on FPGA, but if you don't have FPGA, you can also directly run it on your hardware or your laptop via a hardware simulator. There are a few highlights here, but one of the interesting fact is that VTA together combined with TVM gives you a completely open source stack, from high-level model to compiler optimization to driver to hardware design. That allows us to ask interesting research questions, like how can we develop new machine learning algorithms that optimize for hardware microarchitectures, or how can we co-design hardware microarchitecture together with the machine learning. So we have open source TVM about 3 years ago, and up until now, we got quite a lot of contributions from different companies and academia. And it's been used in productions in many companies, including AWS, Facebook. If you are talking to Alexa, actually the wake word recognition algorithm is optimized by TVM nowadays. It also enables quite a few new interesting research frontiers. For example, there are interesting ideas on how do we design high-level differentiable programming RLs in terms of programming language. There are research groups designing new ASICs and hardware variants using VTA and TVM. And there's a group in Berkeley trying to use here and enable trusted enclave support and to support privacy-aware machine learning. And as we mentioned before, AutoTVM is ideal testbed to test automatic optimization, Bayesian hyperparameter tuning, and other tasks. And this is really an interesting testbed for testing ideas on ML4 systems. And there are we have organized 2 community conferences. You can go to tvmconf.org. There are a lot of interesting talks and slides online if you're interested in tracking out. So far I've talked about 3 systems, XGBoost, and MaxNet, and TVM. I'm going to spend maybe last 5 minutes talk about what are the potential future directions that we can work on. First of all, if you look at TVM so far, what we really do is we have a specified model and hardware backend. The goal of AutoTVM is to be able to define a search space of tensor programs, and we'll try to give you an optimized program that optimizes for that particular model and hardware backend. On the other hand, we can broaden the search space so that we can build an even much more full stack approach that defines search space on both model, program, and hardware variant, so that we can jointly optimize these 3 variants to give you a combination of model, program, and hardware together. In order to do that, we really want to be able to design full stack machine learning models that is aware of all those system optimization and bring machine learning as a first-class citizen in each component of those of the machine learning stack. We believe TVM is a very nice first step towards that. More broadly, there's an interesting question of how we can start to think about more broader life cycles of these intelligent applications. In particular, if you look at modern learning system, normally you will just take a learning system, train a few data set, learn a model, then you deploy that. On the other hand, if you start to look at more like program optimization and other cases, you can find that it's a bit more interesting. So the learning system will try to interact with the environment, where you will have new data being collected. In the case of program optimization, there will be new workloads like new machine learning models coming in, and there'll be new models and even new kind of tasks. Like we started by optimizing computer vision, but then we started optimizing NLP workloads. The question is how we can build a more lifelong system that sustains this kind of model evolution. And there are challenges like how we can do model transfer as model complexity grows, how we can smartly acquire data, and how we can build real-world learning system as a test bed. We believe TVM is quite an interesting step towards that. So to recap, in this talk, we try to talk about elements of learning systems. In XGBoost and MXNet, we really demonstrate that we want to build learning systems that are accessible to people, so that data scientists don't have to worry about data cleanups, and that are scalable, so we can train bigger neural networks on limited GPU memory. In TVM, we have shown that it's really important to bring intelligence to those learning systems as well, so that they can automatically optimize for themselves. And finally, all those learning systems will start to become full stack, so that we can co-optimize the hardware, model, and system together. And we want to start to think about the life cycles of learning system, so that we can optimize for better performance over the duration of lifespan, as opposed to doing everything from scratch each time. So with that, I would like to conclude my talk. And thank you again.
Great, thank you, Tianqi. If there are questions, please raise your hand or just type a question into the group chat. I might start with a couple of questions. So you mentioned that running an experiment basically takes about a second or so.
Yeah.
So you run this configuration, you measure the running time. So in practice, how long are people willing to tolerate a compiler optimization? If I'm going to compile something on your hardware, in practice, do people tolerate like an hour? Do people tolerate like 2 hours, 3 hours? Like in practice, in your experience, what is the tolerance?
That is an excellent question. So in this case, because we are doing machine learning compilation, it's a bit different from traditional compiler. In the sense that if you are doing GCC, I don't think people will tolerate more than a minute even on that compilation. But on the other hand, in our cases, imagine that you are deploying a machine learning model on your mobile device for a month or even a year. Then it's totally fine to tolerate 1 day's optimization even to get that extra performance. Besides that, what we can do is we can try to cache those training data, and that's exactly one of the things that we're working on in Optimal, is that we're building infrastructure to proactively collect data and cache them on so that when you are hitting a workload that are already being seen before, you can directly pull out the optimized model, or we can directly learn a more robust cost model in the beginning, so that you don't have to spend as many time collecting data. So there are a lot of interesting workarounds on this problem. But the overall answer is that machine learning applications give us an interesting scenario where people can tolerate a bit of time for better performance. But it will be also great to reduce that time to a matter of a few minutes if possible. Yeah.
Sure. Okay. So at Caltech, a lot of people, of course, are interested in AI and machine learning, but they also work on engineering and science applications.
Yeah.
On the engineering side, the canonical example is a drone, right? Where not only is the computational time is important, but also, I guess, other resource costs like power, or if I'm designing my custom hardware, I might even say, if I were to use this, like, let's say I'm designing my own drone, I want to figure out what is the best performance I can get with different hardware choices, different mobile.
Exactly. Yeah. Yeah.
Have you guys thought about that type of scenario before?
Well, yeah, I think this is exactly what TVM can offer, in a sense that because we can automatically optimize for different kind of hardware backend. Now you can ask, if I want to deploy my model on, if I just want to deploy a model for a budget, say how many amount of dollar you want to put in your board, what is the running time budget you have, you can try to go and optimize for different hardware backend and see what is best, what fits best for you. There's also a question of, if you want to design specialized hardware like ASICs, Another thing that we can do is we can hook up hardware simulators onto the TVM runtime system.
Okay.
That means that you can directly measure the potential future hardware designs and use that in your automatic optimization loop. Also, the hardware simulator will certainly be slower than the running on real hardware. So that would be, you might need more smarter approaches that requires fewer data points. But it's definitely something that's doable.
Okay. And then on the science side, for example, let's say an astronomer is interested in using some of these methods, and they process, an absurd amount of data, and they have issues with memory storage and data storage and data processing, things that maybe are very related to deep learning, but not exactly deep learning, but maybe more related to maybe what Apache Spark might offer.
Yeah.
But are there aspects of your research you think might be applicable to optimizing that type of workflow?
Well, I think that in many cases, for example, if we are looking at scientific data, in many cases, if you want to do, if those machine learning workload reduces to things like distributed linear algebra, I would imagine that we could use similar approaches to optimize the distributed linear algebra. But in this case, the optimization knobs may not be the low-level code choices, but more about the communication and how you distribute the data and different ways on running the communication protocols. Yeah.
I see. Yeah. So basically, if you have like a 100 array antenna of telescopes, because most telescopes these days are arrays, they typically do pre-processing on each telescope individually before.
I see. Yeah.
So there are many design choices there. You can imagine the exabytes of data being generated there.
Yeah.
Are there any questions from the general class? Please raise your hand or type in the group chat. Yes, question.
I have a question about the AutoTVM. You mentioned that there is a step to estimate the statistical cost model, and you mentioned it is similar, somewhat similar to the hyperparameter tuning. So I think it's f hat. Like base optimization, we will use some UCB bounds to estimate that, like what I mean is like the cost model maybe have some variance. So is this important to estimate that, or?
That's an excellent question. So actually, we did experiment with what we call the UCB bound or the expected improvement bound in our optimization process. And what we find actually in our case is that the variance estimation is not as important, as probably because we can collect a lot more data. So that if you go and check our newest paper, there's a comparison between the EI-based approach versus the vanilla-based approach. Another potential reason is that we are already doing epsilon gradient exploration, so that some of the variance is already captured by that part of the process.
Oh, okay.
Any other? Oh, here's a question. So there's a question on task invariance. Usually, how fine-grained are those tasks? This is in the chat. And is invariance coming from certain backbones in the hardware that contribute most of the cost function?
That's a great question. So in terms of task invariance, it really depends on different kind of tasks. Many of them are still very similar. For example, if you look at convolution neural networks, each layer of convolution neural network is a separate task. But basically, for each of the tasks, if your convolution's input shape is different, it's a different task. So in that sense, it's kind of quite similar. On the other hand, you can also imagine a more far apart task, like we might have one task as a convolution operator, another task like a matrix multiplication operator. In terms of invariance, a lot of invariance are actually in the cost model. So the idea is how we can design a cost model that can model your matrix multiplication workload together with the loops that occurs in the convolution workload. In many cases, you might have different level of loop now, so you need to do some smart feature engineering or modeling to be able to make your model be agnostic of those choices.
And just a quick follow-up question, and do you have an automated way of defining a task? or is it pretty obvious from the way that these learning systems are designed?
Well, in terms of task definition, it's actually quite clear in the sense that, for example, one example task would be something like, say, matrix multiplication with, 100 by 100 matrices multiply another 100 by 100 matrix. But you will replace that by convolution with the input shape. So usually, operator plus the input shape will fully specify that task.
I see. It's not like query optimization in databases where somehow the tasks have dependencies across them.
No, not really. Yeah.
Okay, I see. Okay, makes sense. Okay, great. Thank you again, Tianqi, for this really wonderful talk, and take care and stay healthy.
Yeah, glad to be here. Yeah.
Bye-bye.
Bye.